So welcome to Co-17A. My name is James. I am one of the math specialists. I'll be teaching this class. We should probably go through the syllabus. It's not too complicated, but there are a few things I should point out. And then after we go through the syllabus and you ask if you have any questions, you're welcome to ask them. And then we'll jump right into talking about functions and what makes a function and all the kind of stuff you're doing in your classes. Actually, and before we get started, by a show of hands, who is in, let's see, who's in Zhao's class? ZHAO. Okay, a few of you. And I think the other instructor is XU, Zoo. I'm not, I hope I'm saying that correctly. Is anyone, let me double check. Actually, let's take a look here. So we look at the dashboard. Oh yeah, we have, so for 17A, we have, let's see, there's me. We have who's in Alameda's class? Couple, 3, 4 people. And then we already said Zhao. And then, yeah, XU. Who's in XU's class? Okay, so it seems like a even-ish split between the 3 classes. Kind of ish. Close enough that I'm sure it'll be extra challenging to make sure all the classes hopefully stay in a similar-ish place through the content. But that's kind of the dream that never happens. So you'll probably get off from each other, and we'll try to kind of keep abreast of what's going on relatively the same pace. But occasionally I might be ahead of where your class is or behind where your class is, and that's totally fine. Excuse me. So let's go ahead. Actually, I didn't mean to close that. Let's go back ahead and look at the syllabus. Oh gosh, where's my cursor? It's over here. Okay. There we go. So let's go ahead and look at the syllabus for our class. And something I always like to point out to students, just because I think it's something worth knowing, is on Canvas, if you hit these 3 little dots here, you can change both the color of the thing and also whatever it's called. So I like to write, for example, I like this color. Oh, don't do that. Well, so I like to write, Co-17A, the day and time that it meets that, but you can write whatever you want there. So if you have the desire to, you can certainly change that whenever you want. I guess I'll change it back to blue later. Okay, so currently, this is our Canvas for Co-17A. It's currently set to the syllabus of the homepage. I'll probably change that by the end of the week to be the modules because that's where anything useful is really found for this class. But let's go through the syllabus hopefully as quickly as possible just to make sure we've said all the important things. Then we can talk about the modules and then we can talk about. Again, if you have any questions, please don't hesitate to ask. You're welcome to call me James. If that is uncomfortable for you, I totally understand. You also can call me Mr. Parmenter. It's just a lot more to say than James. So James is easier, but Mr. Parmenter is also fine. Let's see what we've got here. So this is the class and time. You're all here, so you know where it is. You're encouraged to come to class in person, and we'll talk more about who is required to come to class in person in a minute. Yeah, you can attend via Zoom. No one's attending via Zoom currently. So to that end, I will be recording the classes. And everything you see up here will also be recorded and put on YouTube and Canvas at a later date. So if you can't come to class, you certainly can still access the content from class at any time that's convenient to you. Let's see what else here. This is kind of blurry over here. Again, my name is James. The best way to reach me is by email. I would prefer you just email me directly as opposed to using the Canvas inbox tool because those emails get sent to like a different folder for me. That's why I don't see them quite as easily as the ones you just send to me, but eventually I'll see the email you send me if you send me an email. You can try calling me if you need to get a hold of me. That's probably not going to work. It used to work, but now that we have now our phones, we don't have phones anymore. We have Zoom is our phone. It's like we're supposed to have Zoom open in our office and someone can call you on Zoom, which I never do. So calling me probably isn't. Just email me if you need to get a hold of me. Really is the right answer. Email me if you want to get a hold of me. I will definitely respond. Or you can come by my office if I'm there. It's 2244 Dutton Hall. Or the best way to find me if you need math help is to come to office hours. Let's go ahead and look at the office hours since we're already there. My office hours are kind of all over the place this quarter. I would say them to you, but really it's kind of a lot. So Mondays, 10 to 11 in CADS, which is the Center for African Diaspora Student Success. And then 1 to 4 in drop-in, which is the lower level of the library, like where all the math, chemistry, bio drop-in is. Wednesday, same hours, 10 to 11, but then 10 to 11 is in drop-in and 1 to 4 is in C class, which is the Center for Chicanx Latinx Academic Student Success. Finally, on Friday, 1 to 4, back in CADS again. And then Tuesdays and Thursdays are more regular in that they're at the same time and place, 1:30 to 2:30. So right after this class, I'll have office hours in CADS, which is right over there in the south silo on the second floor. You're all welcome to come and ask questions about any math thing you want. If you don't know where any of those places are, I guess I could, so as I just said, CADS is right there. C class is above the coffee house. If you like go up those outside stairs, but where the flagpole is kind of, and just veer to the left, you'll see it. It's right there. It's hard to miss. So those are my office hours. And honestly, if you need to find me, you should just look at them there because I'm going to be looking there to be like, where do I go today? Okay, today it's here. Back to the syllabus. So the only thing that's really a minor challenge in this class is the grading, which we'll talk about right now. The grading is pretty easy. It's based on attendance. Who should be worried about the grading? Only those of you that have actually enrolled in the class using the CRN. So if you signed up through Schedule Builder using CRN 55332, then you need to be concerned about what I'm saying right now. If you didn't, if you got added to Canvas by me, by filling out a Google form, or by emailing me, none of what I'm about to say applies to you. You don't have to come ever. But for those of you that are trying to get a workload unit for this class, which is great, you do need to come in person, and the passing grade is 70%, and 70% of 20 class meetings is 14 times. So you have to come at least 14 times. That's it. And I guess I should say, you have to come and like participate, be actively engaged. You shouldn't be like not paying attention at all. So that's all I ask is you come, be engaged, pay attention. And that's what that's what you're here for anyway, right? You're not like here to not pay attention. Why would you come? You could just not come. And then, oh yeah, and to that end, we'll have the attendance form. So hopefully all of your names are on this. If you're in the Canvas, you're on this, whether or not you're registered for the class. So all of you who are here, please do write your name next to your name that should be on there. It's alphabetical by last name. Yeah, everyone will see a grade in Canvas. Again, if you're not enrolled, that grade doesn't matter. If you are enrolled, that grade does matter. Are there questions about that? Yes.
I am currently enrolled in class.
Sure.
What are the advantages of being enrolled in class if you have to worry about your grade?
You get one workload unit.
Okay, what is the workload unit?
It's a unit that counts towards being a full-time student, meeting the minimum progress requirements for financial aid. And that's it. Oh, but it does not count towards graduation. Okay. So really, the only people that absolutely need to be enrolled in this class are those that need the one unit to make sure they're at 12 units for the quarter. If that's not you, you could just as easily drop the class and email me and get added back to Canvas and have the same access as everybody else. The only reason I would ask you to not do that, and it's not that I don't care that much, I care a little bit, is that when we register for rooms, it's the rooms we get are based on the registered student class size from previous years. So when we have a class where there's like 10 people registered, but there's like 40 people coming, it can be somewhat difficult. But if you're like, hey, I don't need the unit and I don't want to worry about having to come, or what I'll probably actually do is like right before the drop deadline, I will email everybody and remind you like, hey, if you're registered for this class and you think you might not pass it because you haven't attended enough, you might want to drop it and then we just get back added into Canvas. So something to think about. You don't need to do it right now, but before the drop deadline, certainly something that'll come back. Five side hand over here. Interesting. Okay, so I think we have. Let's actually go ahead and look and see what else is out there. So this is our website, tutoring.ucdavis.edu for the AATC, which is where I'm a math specialist at the Academic Assistance and Tutoring Centers. We look down here. Scroll down a bit to the co-classes. We have one for 17A, 17B, 17C, 17C. We do have one for 19A. So here's the issue your advisor might have encountered. Unfortunately, because of some stuff like 20 years ago, all of these co-classes that you've enrolled in or not are titled 16A or 16B or 16C, unless you're doing the 21 series. But all the 19 co-classes and all the 17 co-classes, the title on them in the class search tool is 16. So they might just not have realized that this wasn't the right one for that. So you're obviously welcome to stay right now, but you're also welcome to not stay if you don't want to and sign up for the 19A one. The 19A one, while the material will be fairly similar in the beginning, it's going to diverge somewhat, actually fairly quickly. I think the material they do quite a bit of different stuff. So if you're taking 19A and not 17A, I would recommend taking the co-class with Ryan if it works your schedule. It's Monday, Wednesday, Friday, 9 to 10 in Dutton Hall. So that's certainly something that'll probably be a better fit. All right, other questions? Okay, so hopefully the grading is clear. If you're enrolled, registered for the class, you have to come in person. In person. You can still, that said, you can still attend other ways. You can attend live virtually if you want to, especially if you're not feeling well. That might be a great way to attend. Or if you are not able to do that, you can also watch the recording later. And if you do that, either of those, I would beg of you to please fill out this form every time you attend in a virtual way. It just is basically an attendance form. You write your email, your student ID number, your first name, your last name, as it appears in Canvas. It makes it easier for me later. And then which class you're here for. Obviously, it's Co-17A. And then how you attended. I don't know why I have that there still, to be honest. It's not really that important anymore. And then the class date you're marking the attendance for. So let's say that you weren't here today, and then on Saturday, you watched the video for class today. The date you would put in would be, somewhat annoyingly, 4/1/2025. Please do put in the whole year. Otherwise, the data doesn't sort well later. So whenever you attend virtually, I would ask you to do this. The reason we do this is because part of my job is to keep track of all the students that we serve or that I serve, and then report that data to my boss, who reports that data to, I think it's COSAF, which affects some amount of funding that we get during the year. So accurately reflecting how many students we serve is important. So please, 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 if you attend virtually, fill this out. I would also say I would rather you attend in person. I'm glad there's so many people here. I like having a classroom full of people. I think it makes it easier to teach and easier to kind of engage with everyone. So come in person if you can, or if you have to because you're enrolled in the class, and that would be great. What else do we have to go through here? Let's see about this class. If something outside of class is impacting your success in math, please don't hesitate to talk with me about it. I am a resource. I feel like I should change the word there. I am a resource for you, not just want to be. I am. If something in class is said by anyone, including myself, that makes you uncomfortable, please talk with me about it, or someone else if it is me saying a thing, which has never happened in the past, so I'm not too worried about it. But we just kind of say this to make sure that everyone's like, yes, there are resources in case something. This is also true for your other classes, right? If something is happening in another class, which is really why we write this down, you should say something or talk to someone, and we can help you get it sorted out, or at least figure out where to get sorted out. Yes, we know when the live class is. It's right now. So someone did point out that I had this wrong the other day. I had accidentally written Monday, Wednesday, Friday. Thank you to whoever it was that told me that so I could fix it before class met today. The class will consist of me showing you examples, hopefully having you work on examples. My personal goal this quarter is to kind of go back a little bit to giving students more time to work on their own on problems as we kind of go along. It's a little bit challenging in this setting because I'm trying to also kind of, this recording, right? I don't want to have like a lot of dead air. So but I don't think that's like, I can also edit that out later. So it's not like a huge deal. I'm going to try my best to give you all some time to actually like work on problems, either individually or together. And that's kind of the way it's going to work. I'm going to show you things. You're going to do things. You're going to ask questions. I'm going to guide you along to help finding some solutions, and so on and so on. What else? Oh, yes. Please come prepared to work on math problems with some sort of writing utensil and stuff to write on, whether that's pen and paper, pencil and paper, tablet, whatever you like. Your active participation is expected, which is sometimes not as active because I talk too much, and I will try to talk less. Accommodations. If there's something I can do to improve your ability to succeed in this class, like talking slower, please let me know. Students in the past have told me that they really would appreciate if I used a thicker pen, so I do. I used to like writing in a finer pen point, but it was harder to read what I was writing on the board or on the screen. So if there's something that seems like, yeah, James, could you do this? I'm happy to do it. I just need to know that you need me to do it. What else here? To that end, my handwriting is legible. That's about the best compliment I could give it. It is usually legible. That said, if something isn't legible, just ask. I'm not offended that my handwriting doesn't look good. I know it doesn't look good. It's been a number of years that I've not had good handwriting, but please just ask, and I'm happy to clarify things. Yes, the attendance form is making its way around. What else here? If you have accommodations to the Student Disability Center, please have them send them to me. Again, in this classroom context, they're usually not really that necessary because there's no exams and I'm recording everything already. But that said, if there's something you need that I can do for you, that is an accommodation you require, don't hesitate to get that. What else here? Zoom instructions. I don't think anyone needs those anymore. I should probably not write those in the future. But again, you're welcome to attend via Zoom if that is something you want to do. Again, as long as you're not trying to get a unit for the class, you need to come in person. I did change that recently because I was finding that people were just not coming in person. And while that's fine, if not enough people come to class in person and I'm teaching to like 3 people, the dynamic isn't there. It's a better dynamic when there's a full classroom of people. So please do come in person if and when you can. As far as the notes about the class, one workload unit, which we already discussed. You can use the discussion tab in Canvas, which no one has ever done when I've taught this class. So I keep trying to make it work. No one wants to do it. But it is a place where you could ask questions and anyone in class could respond. And I can respond as well. And the added benefit there is that it's really easy to type in nice mathy kind of symbols there because you can use LaTeX. So if you asked a question in the discussion tab right over here, I could respond or your classmates could respond and would happily help you out. There's nothing there now, but maybe I'll write something there later. What else here? Each unit in this course is connected to the other units and to prerequisite knowledge. We're going to start off this quarter by talking a lot about, like, it's kind of like all of pre-calculus in a couple of days is kind of what the first week of this class usually feels like. All of pre-calculus is probably a kind of a roundup there. It's not all of pre-calculus. It's a broad overview of pre-calculus things. And then we get into limits and derivatives and all that Calc 1 kind of stuff. But it is important to kind of keep up with the material as you go, right? If you let yourself get behind, it's really challenging to catch back up. So definitely, I would encourage all of you to stay on top of the material. I think there's something in here about successful students usually spending 10 to 20 hours a week on the class outside of the class itself. That's, I think, fairly accurate depending on your instructor. I know there's 3 different instructors. They probably have different things they're asking you to do as far as homework is concerned. I haven't looked super specifically. Let me just ask by class. In Alameda's class, I assume you have homework. Is it collected? Okay, we don't know. That's fine. How about in Zhao's class? Is there homework or web work? Yes, web work. Oh, both. All right. How about I feel like I'm never going to say this person's name right. XU. Can someone tell me how to pronounce XU? Is it zoo? Is it like the Z sound? Okay, that's a challenge. Chew. I feel like I'm butchering it. Good thing they're not here. In that class, is there homework? Is it due? Is it web work? Okay, cool. I'll look at Alameda to see later. So I definitely think it's good that you have homework due, to have a reason to have to do it and not just to do it because you need to do it. So that's always helpful. Yeah, where can you get more help? My office hours, which we already looked at. And then there's tutoring by the AATC staff and students. So we have student tutors that work in the lower level of the library where math drop-in and all the drop-in is for chemistry, physics, biology, stats, econ. I feel like there's something else down there too, but those are the ones I can think of at the moment. So there's lots of tutoring down there. So for all your class needs, if you're looking for some tutoring, that's a great place to go. You can also get help from each other. So you should definitely get to know each other. I would encourage you before class starts on Thursday, talk to someone else, say hi, because the best place to study with someone, or the best resource, is working with each other, having study people in the class so that you can know what's going on, finding someone in your same class. I think that is a great idea, and I would encourage all of you to kind of do that. Okay, so there's the syllabus. Great. If you have questions, I'm happy to answer them. I would also, if you're curious about something, you can read through it yourself. But the main point is you're enrolled in the class, come to class so you can pass the class. Other than that, the rest of it's kind of just there. There's some important information there, but it's just information. On the other hand, the modules are where the actual useful mathematical information is going to be posted, as well as like resources for the class. So eventually, I'll point out this is the, well, I guess we can view it as a student. Maybe. So here's the student view. Here's what you can see. So there's some useful links, the link to the attendance form, which I just showed you up here, not the one I handed out, right? The one that was up there. My office hours, which you looked at, my YouTube playlist, which has all the 17A classes I've recorded over the last, I don't know, like 3 or 4 years. I don't necessarily recommend watching them, but if you're looking for more things to watch, there are things to watch there. The link to the class notes, Grant's website, which is a very useful resource right there. Grant has lots of great handouts. I won't lie, I often just steal from them outright. They're very useful. A lot of the examples I use come from here. That said, it's still a great place to look because if you're looking for more information about something, there are some very useful handouts here, I think. Back to here and then back to the modules. My website, which is not useful at all. It's got my office hours on it, and that's about it. We don't even need to look at it. And then, and then I do have the exam dates for each of your professors here. I just thought it'd be useful to write those. We have Alameda's exam dates and Hugh's exam dates and Zhao's exam dates all there. So if you're looking for those, you can find them there. They're also on your own Canvas pages, but I thought it'd be nice for an easy place to see them. Actually, it's more so I can see them easily. So be like, okay, you have an exam coming up. We should prepare for that. And then that's for later. We'll talk about log, semi-log stuff. And then there's also the chapters of the textbook. If you need them to easily reference, they're right there. They're just PDFs. They're not like, I feel like oh my gosh, what's the word I'm looking for? The actual textbook that's online. There's a name for it. I can't think of it. The one you have through Equitable Access, I think. I think you have to like scroll down to the page and then click on like the next thing to go to the next. If you want to like go page by page, not that you're usually doing that, it's kind of tedious. These are just regular PDFs that you can scroll all the way through. So if you want to download them, you're more than welcome to. And then there's some worksheets over here that I don't think I have talked about. Why are those there? Okay. This is the student view. All right. So yes, worksheets and stuff. And then the other thing that I will add after class today is there'll be another module like right here that has the class recording and the class notes. So while you can find them on YouTube or Google Drive for the videos and or notes, they'll also just be in Canvas, which I think is probably easier to access. Yeah, these derivative worksheets, we're not ready for them yet, but soon. And then there's all this exam prep stuff that I will post later. All right, I think that's about it as far as the class details go. So let me pause and ask if you have any questions about any of that.
No, if I'm waiting to be added to Canvas, I just signed up today, so I'm just making.
Yeah. So so what happens when you sign up is it goes on some Google form, and then my coworker every morning. So I already added people today, so you probably signed up after I added people. So you'll get added tomorrow. Other questions? Supposed to wait. All right, I've waited enough. Okay, so that concludes the class logistics stuff. Also, you're always welcome to ask me anything about the class, really. Except, no. I often get a lot of students asking me about the passing, no passing part, or it says I'm failing in Canvas. Do I need to worry about this? And I'm like, no, you don't, because you're not enrolled in the class. So if you could try to make sure you understand that point really clearly, because I get more emails about that than I care to. Me than that, I mean, you can still email about anything. I will just be like, I thought I explained it well. They should know this. But you really are welcome to email me or find me and ask me questions about anything math related or class related. I'm a fairly open book. I don't actually like talking a lot except when it's about math. So good thing I'm a math teacher. Yeah, I guess we can get started. A few other things. Okay, yeah, that's what it was. So as far as the actual like writing stuff down here, Again, if something is unclear, please don't hesitate to ask. Also, occasionally I do get off screen. Like sometimes I slide the paper down too far and I start writing it down here. If that happens, just tell me to scooch it up and I will scooch it up. I'm trying to just make sure I haven't forgotten anything else. Excuse me. I guess we can get started. So I got some notes over here. Let's take a look. So there's a lot of material in sections 1.1 through 1.3, 4, 5, 6, kind of. 1.5 is kind of special, so we'll hold off on that for a minute. But 1.1 is all about like what are functions, how do we represent them? 1.2 is kind of like all the functions you might need to know about. I think it's called a catalog of functions. And 1.3 is transformations of functions. I think one of your instructors called it new functions from old. It's just about how you can like move functions around or stretch them or reflect them or I forget. I think that's all. There's like 3 ways you can move them. You can shift them, you can stretch them, or you can reflect them. And then 1.4 is about exponential and logarithm. So I guess we'll start at the very beginning, which is section 1.1. Functions. I don't know about these new pens. I got some new pens. Don't know if I like them. We'll see. Sure. So what is a function? Good question. It's just a rule. It's a way of taking an input and getting an output. So here's an example. F of x is equal to x squared plus 1. That's a function. The input is x. The output is whatever that input is, squared plus 1. Typically, the way I mostly think about representing a function is graphically. So usually when I write a function like this, I want to graph it. Say, okay, this looks something like, well, we could plot some points. I don't really want to plot points. We can plot points. If we set x equal to 0, we're going to get, I mean, there's a number of ways to do this, right? I guess we can make a table. So if x is 0, f of x is going to be 0 squared plus 1. If x is 1, f of x is going to be 1 squared plus 1. If x is 2, f of x is going to be 2 squared plus 1. And I guess we could go negative as well. If x is negative 1, f of x is going to be negative 1 squared plus 1, which is also 2. Negative 2 is going to be negative 2 squared plus 1, which is 5. So we plot a few points here. We get 0, 1, and 1, 2, and 2, 5, and negative 1, 2, and negative 2, 5. We have our usual kind of parabolic shape. So there's a function. What to say about this function? Well, what makes it a function? What makes something a function is the fact that each input only has one output. So when we input, like say x equal to 1, we don't get 2 different output values. We just get one distinct output value. A couple other things to say about this function. Well, let's talk about the domain for a second. The domain, which I think of as all possible x values or all possible inputs. In this case, we have no problems. We have no restrictions. We have no issues. The input can be anything. We could plug in nice integer numbers like this. We could also plug in rational numbers, irrational numbers, negative numbers, as we did already, anything you want. So in this case, our domain is all real numbers. There's a few ways of expressing this. Probably the usual way is in set notation, negative infinity to infinity. And in this one case, people often do something even easier. They say, or a fancy R. The fancy R means all real numbers. On the other hand, the range is all possible outputs, which we usually think of as y values or function values. If I look at my graph, I can see that the smallest y value is 1. It never gets lower than that, right? X squared plus 1, the smallest it can ever be is when x is equal to 0, because x squared will always be non-negative. So 0 squared plus 1 is 1. That's our smallest y value. And then they just get larger and larger and larger. We go up and up and up. So we get everything from 1, and we use a bracket to note that the 1 is included, all the way larger and larger and larger. Infinities always get parentheses because they're never included because they're not actually real numbers. They're just saying you get bigger and bigger and bigger, or you get smaller and smaller and smaller, but we don't actually include those because they're not real numbers. One way to kind of say that this is a function is that it passes the vertical line test. So this function passes the vertical line test. What is the vertical line test? The vertical line test is that if we draw any vertical line, it should only touch the function in at most one point. So no matter where I draw a vertical line, whether it's here or further left or further right, it only crosses the function in one point. I should say at most one point. It might not cross the function at all. Okay, let's look at a contrasting example. I try my best not to just say, do you have any questions? But if you have questions, you should just ask them. So please, 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 please don't hesitate to raise your hand, ask a question if you have a question. If you have a question, probably like 5 other people do too. So if you have a question, don't hesitate to ask it. I can often get kind of carried away, keep going and going and going. I try to slow down. So let's look at this next example of a not function. X squared plus y squared is equal to 25. It's an equation. It has a graph. We're going to graph it. Let's see. I'm trying to keep my papers in order. This is always a challenge for me. So you may or may not know, but this is the equation of a circle. This is a circle whose center is the origin and radius is equal to 5. Better. Okay. So we graph this thing. The way I would graph it is by going 5 in each of the 4 directions. 5 to the right, 5 up, 5 left, and 5 down from my center. And then drawing my circle. Whoops, sometimes the circle doesn't look perfect. That's okay. That's a okay circle. So this equation doesn't represent a function. A couple ways to think about that is one way, it doesn't pass the vertical line test. Right? If we draw a vertical line, that vertical line is crossing the equation, the graph, at more than one point, not a function. It fails the vertical line test. I'm going to say the same thing in a different way. Not a function. Not a function because if there's something on there still. Sorry about that. Cool. If say x is equal to 4, what's the corresponding y value we get? Well, let's plug it in and find out. If x is equal to 4, we have 4 squared plus y squared equal to 25. I'm going to try and solve for y. So y squared is going to equal 25 minus 4 squared, which is 16. That's equal to 9. If y squared equals 9, what's y equal to? Well, 3 or -3. So here's the issue. This is why it's not a function. This 1x input has two y outputs. Y gets to be positive or negative 3. In fact, you could think of this point here as the point 4 comma 3 and this point as the point 4 comma negative 3. That's the whole crux of whether or not it's a function. If one input corresponds to one output or more than one output. I would say generally, we think of X as the input and Y as the output. That is usually the paradigm we're working with, but occasionally people flip that around and do it different ways. But for the most part, we'll just assume, if no one is saying anything about it, that the inputs are the X's and the outputs are the Y's. Or in other language, the independent variable is X and the dependent variable is Y. A third way to have said that this is not a function is to just try solving for Y. If you start off with this equation and then solve for Y, we're going to get y squared equal to 25 minus x squared. And then when we try and square root both sides, look what happens. We get the square root of y squared equal to the square root of 25 minus x squared. Yeah, we might as well. What's the square root of y squared? Sometimes. So the thing about the square root of y squared, well, let me ask you a question over here real quick. What's the square root of 6 squared? I know it seems like a trick question. It's not a trick question. It's exactly what you think it is. It's 6, right? It's the square root of 36, which is 6. What's the square root of negative 6 squared? I think it's also 6, right? Because negative 6 squared is positive 36, and the square root of positive 36 is still positive 6. So the issue here is the square root function is a function, meaning that if you have an input, it can only give you the one output, not two different outputs. That's why we don't say the square root of 36 is 6 or negative 6. The square root of 36 is just 6. So the issue here is the square root of y squared isn't just y. It's actually the absolute value of y. Right here, which I kind of skipped over here, but we could have really said, oh yeah, the square root of y squared is equal to the square root of 9. And then the absolute value of y is equal to the square root of 9, which is 3. And then y is equal to plus or minus. Oh yeah, that's where that's coming from. It's from an absolute value. So it is really actually indeed true that the square root of something squared, square root of y squared is the absolute value of y, which is a little tricky, but true. Yeah.
Why would it be absolute value of y and not plus or minus?
Well, the plus or minus is about to come out. So the thing is, if the absolute value of y is equal to 3, then y could have been 3, because the absolute value of 3 is 3. But y also could have been negative 3, because the absolute value of negative 3 is also positive 3. So the plus or minus just ends up on the other side. We get, instead of plus or minus y equal to the square root of 25 minus x squared, we get y equal to plus or minus the square root of 25 minus x squared. And that's where we see the problem. I think of it as a problem when something isn't a function, right? We see the reason why this isn't a function, because y for one x input, you can get either a positive output value or a negative output value. So that's kind of a third way of seeing that this is not a function. So I'm going to say it again. A function just means each input gives you only one output. Passes the vertical line test. When you solve for y, you should be able to get y kind of definitively as just one thing in terms of x. And that's kind of it. So let's talk about the domain and range here. There's a really easy way to find the domain and range. Look at the graph. How far left of the x value? I know I didn't label this well, but the radius is 5. This point over here is 5, 0. This point over here is negative 5, 0. This point up here is 0, 5. This point down here is 0, negative 5. I guess I'm out of room. Terrible. So for this x squared plus y squared equal to 25, we can really see from the graph that the domain is all x values as far left is negative 5 and as far right as positive 5. And the range is the same. The range is all y values as low as negative 5 and as high as positive 5. But what if we didn't have the graph? what if we had something like x squared plus y squared equal to 25, and we decided to solve for y and get plus or minus the square root of 25 minus x squared? Right. In order here. How do you find the domain then? Well, this is where I want to go. Yeah, sure. So if you have a square root of some stuff, that stuff has to be bigger than or equal to 0, right? We can't take the square root of a negative number and get a real result. As far as we're concerned for now, imaginary numbers are not a thing. There's no imaginary numbers. That's not until 17C. But it really, well, I guess technically at the end of 17B, but in the end of 17B and 17C, we really do actually deal with imaginary numbers a fair amount. So they will be a part of your calculus career next quarter, and then the quarter after that, if you have to take 17C. But for now, we want our functions to be real valued functions, meaning the inputs have to give us real outputs, not imaginary or complex numbers. No square roots of negative numbers. So we need the insides of a square root to be greater than or equal to 0. And even though we could probably solve this in an easier way, when I'm solving something like this, I highly recommend factoring. Factoring is the way to go. It's the safest way to do it. This one, you could probably like do some square root stuff, but it's just safe. In fact, you can. But I'm going to show you the way I would do it, which is factoring this. When we factor this, we have to be extra careful. The 5 comes first. Right, so this is the difference of squares. It's 5 squared minus x squared, and it factors as 5 minus x times 5 plus x. Just so everyone's clear on what I'm kind of not saying is, if you were trying to factor x squared minus 25, that would factor as minus 5 times x plus 5. It looks similar, but it's a little bit different. And the way I think of it is whatever thing is first is the thing that comes first. I know that sounds like I just said the same thing over again. What I'm saying here is since it's x squared first, the x is the first thing in the factors. Here, where it's 5 squared first, the 5 is the first thing. More generally, a squared minus b squared is a minus b times a plus b. And then to solve this inequality, I would use the number line. I would always use the number line, unless it was a linear inequality. Meaning if we just had x to the first power. If you have any other powers of x, you almost always want to factor and use the number line. So I'm going to use the number line. And I'm going to put my values of x that make this equation equal to 0. So x could be positive 5, x could be negative 5. And I want to know, is this whole quantity positive or negative? What we usually do is pick a number. Pick a number that's not 5 or negative 5. I always tend to start to the right. So I'm going to pick a number like 7 and plug it in. 5 minus 7 is negative. 5 plus 7 is positive. And negative times a positive is negative. So all I'm saying here is that for any number bigger than 5, it could have been 6 or it could have been 60 million. This whole quantity will be negative. Great. Let's pick something between negative 5 and 5, like 1. 5 minus 1 is positive. 5 plus 1 is positive. Their product is still positive. And again, it wouldn't have mattered if I picked 1 or 2 or 3 or pi or negative 4. Any number between negative 5 and 5 will produce the same result. Because this quantity can only change signs if it goes through 0. Right? To go from positive to negative, you have to go through 0. And 5 and negative 5 are the only values of x that make this thing equal to 0. And finally, one more time over here, by plugging in something like negative 6, 5 minus minus 6 is positive, 5 plus negative 6 is negative, and the whole thing is negative. I'm trying to figure out where this whole thing is bigger than or equal to, meaning I want to include the 5 and the negative 5. I want this middle part where it's positive. So my domain here, not surprisingly, because we already knew the answer, is negative 5 to 5. That's how we could have done it without having graphed it at all.
Same thing for range.
The range is always more challenging. So here the range is, this is not a good example for range. To find the range, you can either do something with an inverse function, which is not the best here, or you can usually look at the graph. Or thirdly, annoyingly, you can kind of try to just, this is going to sound not very helpful. You can kind of try to figure it out. So here's what I mean by that. If y is equal to plus or minus the square root of 25 minus x squared, I'm trying to find the range. Okay, so I'm going to think about, well, first of all, I'm going to remember that x has to be between -5 and 5, right? I've already settled the domain. So I'm going to ask myself, how large and how small can I make this value? So what value of x could I pick to make the square root of 25 minus x squared as small as possible? +5, or actually -5 too. Either one would work. So if I pick x equal to 5, I'm going to get y equal to the square root of 25 minus 25, which is 0. Similar question, what value of x could we pick to plug in that would make this as big as possible? I know you're all thinking it, you just don't want to say it. If I want to make 25 minus x squared as big as possible, I want to make x squared as small as possible. Meaning I'm going to pick x equal to 0. If x is 0, we're going to get y equal to the square root of 25, which is 5. And then over here, for the lower half of the circle, same sort of deal. If x is 5, we get y equal to 0. If x is 0, we get y equal to -5. So we can see that it goes all the way from -5 to 0 and 0 to 5. So our range is also -5 to 5. It's not like a super precise or well-defined method of doing it. It's kind of asking yourself the question, what can I pick for x to make my function as big as possible? And what can I pick for x to make my function as small as possible? And it doesn't always work great. But for now, it's, if you don't have a graph, it's kind of the best way of doing it. Later on, we'll talk about how you can find the range using an inverse function if, and it's a big if the function has an inverse. Not every function does. All right, let's see. Let's look at a few more examples of things. Sure. So just trying to think about which way I want to go here. Yeah, let's talk about more domain stuff. So more domain things. So lots of functions have unrestricted domains. Many functions have unrestricted domains. A couple examples. F of x equal to x squared plus 6x plus 7. Or g of x equal to sine of x. Or h of x equal to 2 to the x power. Each of these functions has no domain restriction. X can be any real number, positive, negative, rational, irrational, et cetera, et cetera, et cetera. Sometimes you get weird outputs based on what you put in, but there's nothing X is not allowed to be. So each of these have domain all real numbers. Negative infinity to infinity. I should say more generally, any polynomial has a domain that's all real numbers. What's a polynomial, you might ask? So any polynomial, which looks like a function of x where the powers of x are positive, non-negative integer numbers. So like we're thinking x squared, x cubed, x to the fourth, et cetera, et cetera, et cetera. So any polynomial, we could write it very generally as like p of x equal to a sub n times x to the nth power plus a sub n minus 1 times x to the n minus 1 plus all the way down to some coefficient of x plus some constant term. As long as n is a non-negative integer. 0, 1, 2, 3, 4, 5, 6, 7, etc., forever and ever and ever. Any polynomial has domain all real numbers. There's no problems, right? X can be anything, no matter what. Because if you're raising x to a positive integer power, any real number squared or cubed or to the fourth power, to the fifth power, etc., is defined. One example, just to make sure everyone's cool with it. It's not my favorite, but that function is a polynomial. It's a very boring polynomial. It's a constant function, but it still technically qualifies. Because what's the power of x there that I didn't write?
1.
It's less than 1. If I was going to write g of x equal to 6x, that would be a power of 1 or a degree 1 or, yeah. But there's no x's over here. And although we never would write it this way, you could write it as 6 times x to the 0th power. It is technically a 0th degree polynomial. But nobody writes that. But it is a polynomial. It's kind of boring. It's just a constant function. It's a horizontal line. It is a function, right? It looks like I'm out of room on this page. What it looks like. But if you f of x equal to 6, no matter what I put in for x, I always get the same y value, right? F of 1 is 6. F of pi is 6. F of 17 is equal to 6. So that if I graph this thing, I just get y values that are 6 the whole time. And x can be anything. It could be 1 or pi or 17, which is way over there. Every y value is 6. Every x value gets accounted for. Right? X can be anything. Y gets to be 6. This is actually, I will pause for a second here. This idea actually becomes a little bit important in future quarters in that when I look at this equation, which I would probably actually think of as this, when I'm graphing y equal to 6, I'm noticing what's missing. There's no x. And usually if a variable is missing, it means you have freedom in that direction. So when I graph y equals 6, I'm like, well, y has to be 6, but x gets to be anything because it's not, there's no restrictions on it. It's a free variable. That idea does come back in later quarters. Okay. What time do we end at? 1:30? 1:30. All right. Making sure. Don't want to go over. So that said, I think that clock looks about right. Yeah, okay. This is right. Sure. I shouldn't go over, but if it's like 1:30 or if it's 1:30, 1:31, and I'm still talking, say something or start leaving, it's totally fine. I don't mean to go over. I just sometimes get excited about the math. So, all right. So those are some functions that don't have any domain restrictions, but then there are functions that do. And in my mind, there are 3 types of functions that have domain restrictions. Well, okay, technically there's 4, but there's only 3 we're going to worry about right now. Domain restrictions. One type of function is f of x equal to some sort of quotient. I don't really care what's on top, over some stuff on the bottom. And in this case, right, literally, right, I'm going to write the words I said. I don't care what's on top. I care what's the stuff on the bottom. In this case, we're going to start off by saying, well, the stuff on the bottom better not be equal to 0. We can't divide by 0. Doesn't work. And to be honest, actually, what we usually do is we say, to be really frank, we exclude where the stuff on the bottom is equal to 0. Because it's usually easier to think about solving that equation instead of solving this non-equation, this inequality. We'll do some examples in a minute, but I want to write down the 3 things here, and then we'll talk about some examples. The second thing we have to worry about is one we already did. It's if our function is the square root of some stuff. Square root's actually a little too restrictive. It can be any even root. So square root or any even root, 4th root, 6th root, 10th root, etc. Then we're going to say that the stuff has to be greater than or equal to 0. Right? It's okay for the stuff to be 0, right? We can take the square root of 0. The square root of 0 is 0, but it can't be negative. We can't take the square root of a negative number and get a real result. Thirdly, the other kind of function that has domain restriction is a logarithm with whatever base. Doesn't matter what the base is. That doesn't change the domain of a logarithm. If you have a log of some stuff, the stuff that you're taking the logarithm of has to be strictly greater than 0. We'll talk more about this probably tomorrow. Then if I say tomorrow, I mean the next time I see you all. The next class meeting, we'll talk about why the logarithm's domain is what it is. But for now, you can just believe me that yes, for a logarithm, we can't take a log of 0 or negative number. So these are the 3 types of things where we have to worry about domains. If you don't see one of those 3 things, with one small exception, if you don't see one of those 3 things, you're probably free and clear to say the domain is all real numbers. So when I'm asked about domain, I'm like, okay, is there a fraction? No. Is there a square root? No. Is there a logarithm? No. Cool, I'm done. Domain's everything. But if there is one of those things, that's when we have to be a little bit more, or do a little bit more inspection. Yeah. So let's look at a few examples here. I'm sorry. Plenty of time. Let me keep this up here, actually. So, some examples. Let's say our function was equal to, interesting. Yeah, so let's do that. 3x minus 6 over x squared minus 5x minus 24. And I want to find the domain. Well, I see a fraction, a quotient. It's technically also called a rational function because it's a polynomial divided by another polynomial. So I will just point out, note, f of x is a rational function. Meaning a polynomial divided by another polynomial. So we should be concerned about where we might accidentally be dividing by 0. So to find the domain, we want to exclude any values of x where exclude is not a spelling class. We want to exclude any values of x where x squared minus 5x minus 24 would be equal to 0. Those are the only things we are worried about. Anything else is fine. But those values of x, there's probably 2 of them, are problematic. So the way to solve this is by factoring. Well, I should say, the way to solve this is hopefully by factoring. If it's a quadratic equation and it doesn't factor easily, you can always use the quadratic formula. I don't want to use the quadratic formula because it does factor, but if it didn't, I would. This is going to factor as x minus 8 times x plus 3. Because negative 8 times 3 is negative 24, and negative 8 plus 3 is negative 5. And then we can see I want to exclude where x minus 8 is equal to 0, or x plus 3 is equal to 0. Or in other words, I want to exclude x equal to positive 8, x equal to negative 3. Those are my 2 problem points. So my domain is everything except for that. I often like to draw it on the number line. The number line is great, by the way. The number line is something you should use like all the time, whenever it makes sense to. If I put an 8 on there and a negative 3, I don't want those 2 numbers, but I literally want to include everything else. So I want my domain to be everything from negative infinity to negative 3, excluding negative 3, union everything from negative 3 to positive 8, excluding positive 8, union everything from 8 to infinity. be careful about this, right? If I'm starting at like parentheses 8, that doesn't mean I'm starting at 9. Right? I'm starting like at 8.0000000, as many zeros as you want one, right? Like I'm starting right next to 8, not at the next integer value. So that's our domain. Oh, sorry, I was loud. That did not mean for that to be so loud. Something I want to point out. I think it's kind of worthwhile. So a side note here. This other function, g of x equal to x minus 8 over the same denominator. Okay, here's a good question. I think. Maybe. Does this function have the same domain? Let's have some thumbs. Thumbs up for yes, thumbs down for no. Same domain or different domain? Yeah, it's a thumbs up, right? Even though we could simplify this function and cancel the factor of x minus 8, that doesn't mean that the domain still gets to include the 8. The 8's a problem whether or not we cancel it. In fact, if we were to simplify this as x minus 8 over x minus 8 times x plus 3, if we cancel the x minus 8s and say it's 1 over x plus 3, we have to write ourselves a note and say, but x can't be negative 8. Because if we plugged in negative 8 in the beginning, we would have gotten 0 over 0, which is a problem. We'll talk more about 0 over 0 a lot. So the thing I'm trying to point out here, which I'm taking the longest time to say, is that when you're finding the domain of an expression, you don't want to simplify it first. You want to leave it unsimplified and just worry about the parts that we have to worry about, either the denominator or the thing inside the square root or the thing inside the logarithm. Cool. Let's look at something else. Yeah. Sure. Let's do one other example here. So let's talk about the domain of f of x equal to 3x plus 4 over x squared plus 49. So same kind of deal, kind of. I still see a rational function. And if I'm talking about domain, I'm still worried about where the denominator might be equal to 0. So I'm going to start off by saying, well, for the domain, I'm going to again exclude x squared plus 49, which is the denominator, equal to 0. And normally I would try to factor this. That's my usual go-to, but this doesn't factor. It's not x plus 7 times x plus 7. I'll point out, just in case that's unclear, x plus 7 times x plus 7. We FOIL this out. We get x times x. We get 7x and another 7x for 14x. And we get 7 times 7, which is 49. They're not the same. This doesn't factor. Or I should say, it doesn't factor using real numbers. It does factor if you use imaginary numbers, but that's not what we're doing here. Or if you tried to solve this, right, you could go the other route. But then that's a problem, because if I try to square root both sides, I'm going to have a square root of a negative number, and that's not real. Right, x is plus or minus the square root of negative 49. Nope, no dice. That's not real. This denominator is never equal to 0. Let's think about it from a more logical perspective. X squared. Whatever you plug in for x squared is always going to be bigger than or equal to 0. Pick any number you like. Do it right now in your head. Pick any number you like. Pick your favorite number. Hopefully it's small. And square it. Did you get something that was bigger than or equal to 0? Even if you picked does anyone have a favorite negative number? Like, right? No one's favorite number is -3, right? That'd be weird. But even if your favorite number was -3, -3 squared is -3 times -3, which is positive 9. So any number squared is bigger than or equal to 0. Specifically, if you pick 0, 0 squared is equal to 0. So x squared is bigger than or equal to 0. And then if I add 49 to both sides, x squared plus 49 is bigger than or equal to 0 plus 49, which is equal to 49, which is definitely bigger than 0. So whatever we pick for x, the denominator is always not equal to 0. meaning we're never going to divide by 0 no matter what x is equal to. So here, the domain is all real numbers. There are no restrictions here because it's impossible for the denominator to equal 0. So something to be aware of. Sometimes that happens where you see a rational function like, oh, well, we have to make sure the denominator is not 0. And sometimes it's just never 0 no matter what we have for x. Sure, we did that one. Yeah.
If it was x squared minus 49.
Oh, that's a totally, yes, exactly. So yes, if on the other hand, our example was, say, g of x equal to 3x plus 4 divided by x squared minus 49, then we would say we're going to exclude where x squared minus 49 is equal to 0. I'm going to factor it as x minus 7 times x plus 7, because it's the difference of squares, not a sum of squares. And there we end up getting x equal to 7 and x equal to negative 7. And then we would exclude those two numbers. I don't want negative 7. I don't want positive 7, but I want everything else. So my domain for this would be from negative infinity to negative 7, union negative 7 to 7, union 7 to infinity. What if, on the other hand, papers? What if, on the other hand, we had, say, something almost the same? What if we had f of x equal to the log base 3 of x squared minus 49? So we're still dealing with essentially the same argument, right? X squared minus 49 is the thing we have to worry about. In the previous example, we needed to make sure it wasn't ever equal to 0. So we just pulled out the 7 and pulled out the negative 7 and said, throw them away, we want everything else. Here, there's more work to do because we're not just solving an inequality. Well, we're not solving a not equal to, we're solving an inequality. We want the insides here, x squared minus 49, to be positive, greater than 0. And this is where, so I will point out, in this previous example, we probably could have done less work. I probably could have just said x squared equals 49 and x equals plus or minus the square root of 49, which is 7. Here, it really doesn't serve us. When you have an inequality that's a greater than or a less than, it really, really, really pays to factor this. So same work, it factors as x minus 7 times x plus 7. And then we're going to put those numbers on the number line so we can see which intervals on the number line give us positive results. So I'm just thinking about plugging in numbers here. We're never picking the number that is actually on the number line. Also, I should point out, I didn't write 0 down. I never write 0 down unless it's one of the things that actually makes it equal to 0. I know 0 is like a nice like middle, but we really don't want to write it down if it's not something we want to consider. So I'm only writing the values down that make this quantity equal to 0. Or said another way, I'm only writing the quantities down where the sign might change from positive to negative or negative to positive. So pick a number larger than 7, plug it in, positive, positive. I don't care that it's equal to something, right? It's what? It's 1 times 15. We don't care if it's 15. We care that it's positive. Between negative 7 and 7, we can pick 0. 0 minus 7 is negative, 0 plus 7 is positive. The product is negative. Finally, over here, negative 8 minus 7 is negative. Negative 8 plus 7 is also negative. And then negative times negative is positive. We cannot do them separately. We can't think about like this part bigger than 0 and this part bigger than 0 separately. We have to combine them together because we are multiplying their values together, which affects the sign of the result. There was something else. Oh, I know what it was. Another way people do this, instead of plugging in point after point after point, which can be tedious sometimes, especially if there's more factors, is we can say, I'm going to plug in the first number here and get a positive. And then this 7 came from that factor. That factor has an odd power of 1. And when the power is odd, the sign changes from positive to negative. Same deal here. This negative 7 came from this factor, which has an odd power as well. And we go from this side to that side, the sign changes. I'll do another example like that to kind of show more what I'm trying to say. With this example is maybe not the best for it. But here, we then have to remind ourselves, what are we asking for? We want this whole expression to be greater than 0, meaning we want the positive parts. We don't want the 7 or the -7, right? Because if I picked 7, that would make the whole thing equal to 0, and I want it to be bigger than 0. So our domain here is everything from -infinity to -7, excluding -7. And then we don't want any of the middle part. We don't want -7 to 7. We're going to start back up at +7 to infinity. I think domain is pretty important. It's good to be able to know when a function is defined, or where, I should say, where a function is defined. When's probably not the right word to use there. Let's look at one more example here. Always a struggle. Yeah, there's enough room, I guess. So let's say our function is, let's make it easy. Well, easy in that we're going to factor it from the get-go. So g of x is equal to x minus 1 cubed times x minus 5 squared times x plus 2 to the 4th power. And we're going to find the domain. Oh, a question.
So the rules that you gave us for the restrictions, we use those to determine what we're plugging the function into, like equal to 0 or not equal to 0 versus greater than or equal to.
Right. So yeah, back to those rules for domain. So it's really just what we're worried about, right? If you have some sort of quotient, we're going to say the bottom part can't equal 0 because we can't divide by 0. If we have a square root, we're going to say, well, the stuff inside the square root has to be bigger than or equal to 0 because we can't take the square root of a negative number. And although we haven't talked about logs as much, when you have a logarithm of something, we're going to say, oh, that something has to be strictly greater than 0 because we can't take a logarithm of 0 or a negative number. Excuse me. I don't like teaching. This is not my favorite time to teach, by the way. I never teach from noon to 1 because I usually eat lunch. So I'm eating lunch like right before this. And so I apologize for the burping, but I guess you'll have to get used to it because I'm going to eat lunch before this class because I'm going to be hungry. So yes. Excuse the burps. So here for the domain. Well, again, the setup is always the same, meaning we're looking at the function, we see a square root, or let's make it a 6th root. I know, that's terrible when teachers, let me just change it real quick. But it doesn't matter whether it's a 6th root or a square root or a 600th root. If it's an even root, we have to think about the inside stuff being greater than or equal to 0. It has to be non-negative. So we're going to say, cool, x minus 1 cubed times x minus 5 squared times x plus 2 to the 4th. It better be greater than or equal to 0. And then we're going to put on the number line all the values of x that make this expression equal to 0. I see +1, +5, and -2. We're going to write them in order as well, right? So make sure you write them in the correct order. Bigger on the right, smaller on the left, more negative further left. So the biggest positive numbers on the right, smaller positive numbers, negative numbers, more negative numbers. The spacing doesn't matter. I have 1, 2, 3, 4 intervals, or always one more interval than you have numbers on your number line. If you have 3 numbers, you got 4 intervals. If you have 2 numbers, you have 3 intervals, right? Because you have one interval to start with, and then once you put a number on there, you're breaking it up into one more piece. So we are going to start furthest right and pick a number larger than 5, and the unoriginal answer is 6. So we plug in 6, positive, the whole thing's positive. And then at the next juncture, you can do one of 2 things. You could either just pick another number. So if we pick something between 1 and 5, like 3, and plug it in, let's see what happens. 3 minus 1 is 2. 2 to any power is still positive. 3 minus 5 is -2, but -2 squared is positive, and 3 plus 2 is positive, and a positive number to any power is still positive. So it's still positive. Or in other words, I looked at 5. 5 came from this factor. This factor was raised to an even power, so the sign stayed the same. On the other hand, this 1 came from this factor, which is raised to an odd power. So we're expecting the sign to change or switch. We can check it though. Between -2 and 1, we can plug in 0. 0 minus 1 is negative, and the negative number to the third power is still negative. It's -1 times -1 times -1, which is -1. 0 minus 5 is negative, but the negative number squared is positive, and 0 plus 2 to the fourth is still positive. So it's a negative times a positive, which is negative. All right. What do we think we're going to have over here? Well, the -2 came from this part. It's raised to an even power. So we're expecting the sign to stay the same. So it's staying negative. We can also check it, right? If you plug in -3, -3 minus, right? In fact, if we look at this thing with a more discerning eye, this part's always positive. This part's always positive. The only thing that's affecting the sign is this part here. If you plug in -3, -3 minus 1 is -4, and -4 to the third power is still negative. Or as I like to say, odd powers preserve the sign. A negative number to an odd power is still negative. A positive number to an odd power is still positive. Whereas even powers make everything positive. They don't preserve the sign. So here, this one's going to be kind of tricky to write out. So we want to include the 5, include the 1, and include the -2. The -2 is on its own little island over there, all by itself. So the way we're going to write that is -2 in braces, union, bracket 1. And there's no stopping once we get to 1, right? It's 1 all the way to infinity. We don't have to stop at 5. When you have a single thing all by itself, this is the correct way to express it. You could maybe get away with writing bracket -2, comma -2 bracket, but you don't. It's not what people want to see. There was one of, yeah, it's going to point out. On the other hand, this function over here, the third root of the same thing, there's nothing to think about. I don't have any domain restrictions. Cube roots, you can take a cube root of anything. So here our domain is all real numbers. That is a 3, by the way, in case you weren't sure. The domain is everything here. Just to make sure everyone's cool with this, what's the cube root of 8? 2, because 2 times 2 times 2 equals 8. And what's the cube root of -8? -2. Because -2 times -2 times -2 is -8. So you can always take the odd root, meaning a third root, a fifth root, a seventh root, et cetera, et cetera, et cetera, of any number, positive or negative. You can take the cube root of 17. I don't know what it is. It's something between 2 and 3. It's not nice. It's irrational, but it certainly is real. There is an actual number. If you multiplied it by itself 3 times, you would get 17. What is it? It's the cube root of 17. There's no better way to say what it is. If you plug it into a calculator, you'll get a decimal approximation, but that's the exact number.
So if the root is odd, then it's all the numbers, and if it's even.
Right. If the root's odd, there's no worries because you can take an odd root of a negative or a positive number. But if the root's even, we can't take square roots or even roots of negative numbers. I'll just point out the cube root of -17 also is a real number. I don't know what it is. It's -1, -2 point something, but it is a thing that exists. It's just hard to express. All right, it's been fun. 1:30. I'll see you all on Thursday. Make sure you got to put your name on the sign-in sheet if you didn't already.